So welcome everyone. So we can start. My name is Professor Philippe Blanc. I'm working for Paristech Armin, and it's my pleasure to chair the breakout session about renewable energy and the showcase related to this showcase 3 related to renewable energy. So a few words about that. The idea of the renewable energy showcase is to provide innovative and mature products and services for renewable energy development and management, leveraging European Earth observation data. And for that, we want to enable collaboration between research centers and private sectors and engage data provider, both data provider and users. This showcase is a contribution to some overall overarching initiative. The first one is about the GEO, Group of Earth Observation Initiative, GeoVener, GeoVision for Energy. And of course, we are tackling the United Nations Sustainable Development Goal 7 about affordable and clean energy, and more particularly the 7.1 and 7.2 goals. And of course, we are also contributing to the European Directive for Renewable Energy goals. From the beginning, we have 3 pilots on board in the showcase, and we will have some presentation from all of them. First of all, the NextSense Solar Energy Nowcasting and Short-Term Forecasting System from the National Observatory of Athens. We have second pilots, high PV penetration in urban area from Armin and DLR. And we have emerging offshore wind products from the Denmark Technical University, DTU. And from we have a new pilot from the onboarding process that took place yesterday. And we are welcome DHI Gras for first pilot wind site, first class input data for wind energy models. So today the session is the following. So we will start with a very short presentation of 5 minutes for this new pilots. Then we will have the 3 pilots presenting for 15 minutes each, more or less 15 minutes each, plus 5 minutes of question and answers. And we will end the session with an open discussion and to write 3 main points to report to the plenary session just afterwards. So this is the first part, and I leave the room to Stelios for doing the presentation about NextSense. Thank you very much.
Sorry, Philippe, is it me or Torsten first?
No, I think.
Sorry, Torsten. Sorry.
Oh, no, don't worry.
Yeah, right.
Well, I'll share my screen and take the word for 5 minutes. We were accepted as a pilot to eShape yesterday in the General Assembly, and I had a chance to explain what are we going to do with the pilot yesterday. The pilot is conducted together with DTU Wind, so this is our partner in the project also. And yesterday we talked about what are we aiming to do in the project. Today maybe I can tell a bit about what are the data and what are the Copernicus information layers that we are using as input to this data package that we have developed called WindSight. So WindSight is our vision to create a high quality, cost efficient information that can improve wind resource estimation. We managed to do this data layers together with the partners that are listed here: Vestas, Vattenfall, EMD, and DTU, DTU Wind, in a project called InnoWind, where we had a 3-year partnership aiming to improve the accuracy and coverage of map layers that can be used as input to flow models. And what came out of this research project and what we are now doing a pilot on in eShape is this data package called WindSight. So in the pilot in eShape, we'll be looking at how can we increase the uptake of windside data and windside layers for the energy community, and especially the wind modelers and wind community. The product that we have developed in this InnoWind projects are land cover products tailored for wind sites anywhere in the world, and some forest height and density products also for improved surface roughness estimate for wind models, and a data package on historical and future changes on wind sites, as well as information layers on elevation data and advanced softness roughness. And most of these data are based on Copernicus and are readily available for wind models. So they are tailored to improve the wind resource estimation. So I'll show you a few of these products, and then what I think would like to get out of the eShape is good connections within the energy sector. So the people who are in this session, please reach out for us for taking part in this pilot as part of a user community, or whether you have connections or contacts to us. So we would like to hear from you. And you can reach out to me, who is sort of the pilot project owner, or our partner in DTU Wind, and we can see how we can engage you in this pilot. Just to give you an example of what kind of products we are looking at, land cover is a sort of standard remote sensing product, but we have developed this to be more tailored towards the wind community, with sort of specialized land cover classes, and can deliver this anytime all over the world for these wind sites. So an example is shown here with a satellite image that is converted into a product suitable for the wind industry. Here the special focus is on forest and roughness that these forests create for the wind modelers. Also, we have looked into forest height and density, and to give you an example of what comes out of such a research project, this is a sort of a forest height product that we have developed in this InnoWind product, and that is now repackaged into the windside data package. So I think I will not take too much more of the time here today, but urge you to contact me if you want more information about the pilot. Especially, I would like to sort of reiterate and say that what we aim to do is we have this data package that has been developed. So we have an existing service, existing layers and data information. And with the pilot, we aim to increase the uptake and the commercialization of this data package in using eShape and the partnerships and tools that are made available in eShape. So if you see that you can contribute to this, and we more than welcome you, especially in this energy forum, to reach out to me and our technical partners, DTU, to take part in this process. So I think I'll end here and thank the chair for allowing us to speak today. Thanks.
Thank you very much, Torsten. Right in time. So now it's indeed the time for Stelios for doing his presentation about NextSense. So 15 minutes and 5 minutes question and answers.
Okay, thank you very much, Philippe. I'm going to present the first of the 3 pilots that belong to the renewable energy showcase. It's called NextSense, Solar Energy Nowcasting, a short-term forecasting system. And I'm Stelios Kazadzis. I work in the Physics and Meteorological Observatory of Davos World Radiation Center, which is in Switzerland. And the presentation is with the contribution of Panagiotis Kosmopoulos and Charis Kondres from the National Observatory of Athens. A little bit about what is the pilot and what is the objective of NextSense. The objective is to develop a system that provides high spatiotemporal resolution solar radiation and solar energy products that are based on Earth observation real-time data and also Copernicus atmospheric monitoring service data and other, in order to optimize or maximize the solar energy use for different user levels or scales, from the private user to the national scale or regional scale. The expected user community is grid distribution operators, grid providers and managers, municipalities, PV photovoltaic parks, and researchers. And after the start of the project, the pilot phases start from the development, evaluation, including upscaling of this NextSense service, the demonstration of the system, including the benefits for the Earth observation use, the co-designing aspect of the development of targeted products with the end users, and also the uptake of the pilot to international scale, including the dissemination outreach activities. The partners are the World Radiation Center in Switzerland, National Observatory of Athens, Greece, Armin and Transvalor from France, and Sedare, an institute from Egypt. Now, in general, the objective of NextSense is through GEOS and related developed tools, to contribute towards the sustainable energy development goal of the United Nations and to contribute towards the GEO vision for coordinated Earth observation information. This is very general, but more specific. And I will refer to each one of them separately. It's to develop this NextSense system, to upscale it, to demonstrate it and deploy further nowcasting and short-term solar energy products, to co-design new products, and to engage new stakeholders and end users. So about the first, the starting point and the first objective to development of the system, I have to mention that SENSE system, which is the, let's say, the father or the father of NextSense, has been developed through the project GeoCradle, that an EU-funded project from 2016 to 2018. It uses different Earth observation information from satellites, different atmospheric, let's say, parameters. Also, it uses other parameters from the Copernicus atmospheric monitoring service. There were a variety of users that used these products that were based in spectral solar irradiance, and there were solar energy related ones, solar ultraviolet radiation related to health and plant growth, and also solar radiation in the visible parts of the spectrum that was related with agriculture. So the next step for this CSA project was to try to include this forecasting aspect, and to do that, we had developed a cloud motion vector forecasting system in order to derive again all this information that I mentioned before. So it's solar radiation energy products, it's spectral irradiance and weighted products that can be anything that has to do with the effects of solar radiation. The spatial resolution is 5 square kilometers approximately, and the temporal resolution is the current solar radiation plus 15 minutes up to 4 hours ahead. And the products can be the horizontal radiation, the direct normal radiation, or calculation in of the radiation in any tilted surface. In order to try to upscale this pilot from a regional or country-based domain to a European domain, on the right you can see the main issue, the main, let's say, limiting factor, which is the cloud product, and that is taken from the MSG satellite. And this circle is the full domain. So for this particular project, it's possible to use the full domain, but for this particular essay project, we use this European and North African domain, which is about 1.5 million pixels that have to be calculated every 15 minutes. Now, during the course of the project, we had some additional collaboration with the Indian University of Technology and the Power Corporation from India that asked us to try to use a different satellite product, the INSAT 3D. You can see the domain, the coverage in the left side. And with this change or with these inputs, we used again this next sense and sense systems in order to calculate solar energy in India. Now the project, the pilot has not only this nowcasting system, there are also other products that you can find in these two web pages. One is the Beyond the Solar Hub, and the other is the Solera.gr web page that is dedicated to just showcase these eSafe applications. You can have access to the presentation and have the links afterwards. And now the main product for this eSafe project till now, it's this forecasting system. So what we did is that you can see that you have this map and you can point to any place in the map, and what you see is with green dots are the solar radiation of the past 3 hours with 15-minute breaks. The blue dot, it's what the solar radiation is in the current time. So using the real-time satellite picture of now or 3 minutes ago to be exact. And the red lines are the calculation of the forecasting of solar radiation in the future using the pictures that have been retrieved through this cloud motion vector system that has been developed. So anybody can go to this page and see different information from different places and also get the data. But in addition to that, the co-designing with the users lead to different kind of other kind of products. It's the nowcasting and the forecasting that I just saw. There are historical data and assessment of some areas in order to be used as photovoltaic parks. Spectral solar data that could be used for other applications, and other products that have to do with the effect of aerosols and solar radiation, and also 0 up to 3 day forecasting of solar radiation. These were not really planned in the beginning of the project, but they came afterwards after the collaboration and the co-design with the end users, and they are still some of them are done and some of them are in the development phase. The end users for this product till now is the independent power transmission operator of Greece that will use directly this NextSense as an energy management system. Is the Egyptian Ministry of Electricity and Renewable Energy of Egypt that has a variety of requests around this product. The Public Power Corporation, again from Greece for renewable energy, that also has a different kind of questions and requests. And two other companies, Sanel, that it's an international company that the collaboration have just started, and Adani Power, which is the work that we have completed with the Indian solar radiation maps that I showed you before. Also have to mention that there are some research projects that are kind of related with this NextSense, and it's this Excelsior EU project that started about 6 months ago and has to do with the knowledge of transfer of this system, among other things, to Cyprus, to a Technical University of Cyprus, and also the ASPIRE project, which is the national project that has to do with characterization of photovoltaics. Now, about engaging related stakeholders, the main point here is that we will try to maximize the horizontal, let's say, availability of tools that the ESA provides with different work packages have to do with this kind of work. So co-designing and end-user tailor-made services that has to do with work package 2. The scientific and technical co-design, it's what is mentioned also in the objectives of ESAPE. And very important, it's of course the access to the coordinated support for user uptake that are horizontally runs ESAPE for different work packages 4 to 6. During the first 18 months of the project, there was also this sprint challenge, and we have chosen 3 of the available options to do that. The first was the increase of the variety of users. This was made through this, mainly through this public power corporation of renewables that had to ask for very specific information and very local pollution information and their relationship with solar radiation, aiming to build photovoltaic parks in places that till now there are other factories that emit aerosols. There was to carry on an action and to boost the sustainability of the pilots, and this action was made through the collaboration with the Indian Institute of Technology and the Adani Power, so using a different satellite source in this next sense system. And the third one, probably the most difficult, is to demonstrate an improvement of the data made available through the DIAS and GEOS platforms. And for this, till now, we just plan to try to, on the 4th quarter of 2021, to try to have access through the GEOS platform system. Right now, everything runs through the GeoGround segment, which is a European Space Agency defined segment for regional data for Earth observation information. Now, the planning for the next month is to continuation of the co-designing and the operational prototype for the end users, to the improvement of the system through evaluation and collaboration with Armin and Transvalor that have already done a lot of work towards this aspect, to identify DIA services and link with the Copernicus atmospheric monitoring services, the finalization of the sprint activities, new user identification, to, let's say, be more into the ESAPE horizontal activities, especially work packages 4 to 6, and the publication of the related science. In the first 18 months, there were some publications. The 2 first one is the presentation at the EGQ conference San Francisco. The second one is the work about the collaboration with the Indian Power Corporation and the Institute. And 2 others are more or less, we plan to submit it till the end of 2020. One has to do with a cloud motion vector system of NextSense, and the other one has to do with the ultraviolet product that is related with Sense and NextSense, and extended validations through European monitoring stations. Thank you very much.
Thank you very much, Stelios. Next presentation, exactly on time. Thanks. So it's time for a few questions. We have 4 minutes for questions and answers. If you have any, go ahead. I think it's possible for the audience to raise and to talk. Any question? So, okay, so I think that's no question. I don't have, of course, because I have all the information from you, Stelios, directly. So we can now move on. We save time to the next presentation. Thank you very much, which is me. Okay, so now it's time for the presentation of the pilot 2 about high photovoltaic penetration at urban scale. It will be a 2-speaker presentation from Wieke Heldens from DLR for the part dedicated to Oldenburg, we'll see, and myself from Paristech. And so before starting the different pilots, the part of the pilots discussion, the overall objective is to develop GIS, graphical information system tools, dedicated to high photovoltaic penetration at urban scale, providing Earth observation data about urban energy system modeling, electric energy demand profiles, and accurate electric production estimation, nowcasting and forecasting of notably fleets of PV rooftop systems. The expected users are the urban planners, grid operators. We think about the DSO, distribution system operators, aggregator for energy trading, and it's a new community coming for managing the energy coming from the urban, from PV systems. And of course, we target researchers in energy and urban planning, and also citizens for the self-consumption aspects. As I said, there are 2 parts of the pilot. The one part is, we said, Armin's part. It's about the PV variability at urban scale, and the pilot is developed in Nantes, which is a city in the northwest of France. And the other part, it's about Earth observation data for PV integration in urban energy system, and the pilot is developed in Oldenburg. The team of this pilot is Armin Paristech, DLR, and also Transvalor Innovation, Solar. And we target to use the supporting infrastructure, which is very important in E-shape, the JAS WKO, and exploring also the urban TEP from ISA. So the objective of the Armin's part of the pilot is to go from the solar cadastre to urban scale variability. Indeed, we have developed a few years ago some already operational solar cadastre with in-sun retrace, and we provide to in-sun retrace some, let's say, static historical based yearly irradiation and monthly irradiation on tilted plants, taking into account what we can see, shadow effects at 1 meter resolution. So if I, no, maybe it's not working, I should have known that. Sorry for that, it's my mistake. So we are coming from this, and we want to take profit of the possibility within the E-shape to provide with near on-the-fly computation of intraday irradiation on tilted plant, taking into account the shadow and 1 meter resolution, and having the analysis of the solar variability, the PV variability at urban scale, not only the annual months of energy you can get from the PV system on the roof. So the data and information access services that we plan to use is the DIAS and the DIAS. So the data used are Copernicus atmospheric monitoring services, providing some elements and information about aerosols, water vapor, and also all sky irradiance, CAMS radiation services. We are using some satellite-based decametric digital elevation model for the orographic shadow effects from, for example, SRTM or Aster. We are using some very high resolution, let's say 10 to 25 centimeter resolution digital surface model coming from here, IGN, with the French National Geographic Institute. And we are using building footprints to locate the roof using, for example, BD Topo, which is also from IGN, or OpenStreetMap. The DIAS we opt for is the Wieke, and the Wieke will help us in this pilot for two parts. The first part is the back office, providing cloud processing that are requested on the fly with OGC Web Processing Services, WPS. This is for the internal computation on near real time, and a front office for the users. And for that, Wieke will host a Jupyter Hub with some Jupyter notebooks that exemplify with Python codes different use cases that we will describe afterwards, with GIS-like interface, web processing services request assistance with graphical user interface, and of course, output data exploitation and data visualization of this computation. So the first use case we want to develop as a Armin pilot is based on historical analysis of PV variability. It's not real-time data, but real-time processing from the historical we have from CAMS, for example, that's starting at 2004, let's say 2015 years of data. And the usage of this pilot is dedicated to PV self-consumption, and it helps, for example, incident interest to size individual system for customers. So we are starting from that is already existing is a solar cadaster. And when you click on your building, you can get the amount of energy you can drive, and you can also size the system with respect to the annual production and annual rentability of the system. But if you couple this information with intraday electric consumption from the customers or from modeling, coming, for example, from the DLR that will be presented afterwards, you can derive for a given building for the customer, including the shading effects on this building, some elements of what is going on inside the day, intraday, and for the different days of the historical, and to compare the electric consumption and the electric production from PV, and derive from this surplus need that has rise from the PV and import needed. And from this computation, you can get the self-consumption ratio and the self-sufficiency ratio that can help the customer to size and to assess the rentability of the future PV system on the roof. The second use case using the historical analysis of PV variability is simulated PV injection in different source points of the electric grid for different scenarios of PV penetration. For example, for distribution system operators like Enedis in France. For example, in the urban area of 1.5 kilometers square, we have 35.
Professor Blanc,
yeah.
Sorry for interrupting.
Yeah.
I will close your camera so we can have a better sound because it's
okay.
it was a bit choppy. Thank you.
Sorry. Yeah, go ahead. Thank you very much.
Thank you.
So if we are considering 20% of PV penetration, this is a scenario, it gets, let's say, 15 hectares of PV roof system, making 20 more megawatt peak. And you can see the map of the point source with the related nameplate PV power injected in this source point. But above all, you can have from this pilot, the stimulation coming from the satellite data and etc. The amount of energy, 5 minutes per 5 minutes for each source point, as illustrated in this animated GIF. And finally, we want to develop a pilot about PV nowcasting and short-term forecasting at urban scale. And for that, we think that's of interest for energy trading with portfolio of PV rooftop systems for example, urban solar energy in France, we will use cloud motion vector coming, let's say, from the pilot one presented by Stelios, and also CAMS aerosol water forecasting and 3D shadowing effects from digital surface model. And here it's a representation of this type of forecasting we can provide. So you get images from satellite. From this, you get a cloud motion vector, and from this, you can do ensemble forecasting. Here it's forecast at, let's say, 11 o'clock up to 1 o'clock. And you have ensemble forecasting deriving from this P90 and P50 values of the future of the production of the PV system. And what is represented here is the performance of such a system with respect to the time horizon. And it's very important to look at the possibility of coupling the satellite information with CMV with real-time in-situ measurements from PV systems themselves. And if we have one or more PV systems that can be retrieved on real time, you can significantly improve the forecast of your system for the point source estimation of the power. So that's all for my part. Thank you very much. And now I leave the room to Wieke Heldens.
Hello, good morning. I will share my screen. Perfect. So I'm presenting the part that we are working on with DLR, and actually we are, even within DLR, we are two teams. We are at the moment with two colleagues, myself and Anne-Catherine Metz-Maroncini from the Earth Observation Center. We are in the team of smart cities and sustainable development. And on the other hand, we have a team from the network energy systems or energy system analysis, where Marianne Schutter-Homscheid is part of. She's the pilot lead, but is unfortunately not available today. And in that team is also Susanne Weyand and Jitro Betke. So we have already two different users or partners here. So an introduction to our pilot. We have the FlexiGIS system, which is a system or a GIS system that models or simulates urban energy requirements. And currently this system is using a limited amount of Earth observation input data, or not using Earth observation data, it's using OpenStreetMap at the moment, but we think it can benefit largely from additional data, and we are therefore looking into different data acquisition possibilities, different sensors from Earth observation techniques. We aim at deriving not only land use data such as in OpenStreetMap, but also all kinds of other input data sets. And then we will test the modeling of the FlexiGIS system, and we will research how this can benefit. So to be clear, the objective is to test and implement Earth observation data into the energy modeling environment of FlexiGIS for the mapping and modeling of the demands on PV systems. And in eShape, we will be contributing to work package 2. What are the new user needs of FlexiGIS users? The users are, on the one hand, the researchers working with the FlexiGIS and interpreting the results. And the results of FlexiGIS are also targeting for example, energy companies. Then we will be contributing to work package 3. How can we make use of EO and especially GEOS products such as and related products and such as UTEP, and also related to work package 3 is which techniques are most promising to use this Earth observation. So we are investigating all kinds of techniques and data. The last year we were occupied with the sprint 1, and we had picked out some challenges. The first one it was about the data delivery of the Earth observation group to the energy modelers, so to say, within DLR, and to test this data to implement it into the energy models into FlexiGIS. So for this, we have a kind of a workflow of the definition of the parameter and the data set it can come from. We prepare the raw data and deliver it to the energy specialist. Then we get a feedback, and if necessary, we can reprocess and then deliver again. And then finally it is implemented, implemented into FlexiGIS. But of course, as this is an experiment or is the first implementation, we need to have some test results and feedbacks, and if it's necessary, we can go back and do this again. So currently we have this list of parameters and data sets we are planning to use. It's a broad range of parameters describing the urban area, and we are focusing on a large range of sources for this as well. Satellite data, EU data products, but also local airborne flight campaigns because of the spatial detail that can bring. So this is the table that comes out of this exercise, more to say. So the first, here on the first line, we have one parameter, it's the land cover, land use, that we have exercised all through the chain. We had some feedbacks, and I will show you results in the end. And then we managed to get it up to that we are implementing it into FlexiGIS. The other products are in the stage of being generated and are now in the first feedback and reprocessing round. And I want to show you two examples. As I said, the land cover product, and I also want to show you the mapping of PV installations. So that is where I start with, because the FlexiGIS can benefit largely if it knows the locations of the FlexiGIS, of the photovoltaic system. For this, we will be trying different approaches, but here you see the results of an airborne hyperspectral data assessment, where we use distinct spectral characteristics to identify the photovoltaic systems. Although not perfect yet, this is a very promising approach because it's quite robust. Then I want to show you the land cover data set. We are starting with the Korean land cover to use this instead of OpenStreetMap. Korean land cover is the Copernicus land cover monitoring service and has a high quality standard all over the EU. So it makes transferability more sustainable. We can apply the model not only to Oldenburg, which is a small city in the north of Germany, but to any place in the EU if this turns out to be a promising data set. And we prepared this data set and already noticed, of course, some differences where OpenStreetMap really focuses on land use classes. Korean is describing land cover classes. And also the level of detail of classes within urban areas is smaller, or there are less different classes within urban areas in the Korean dataset than in the OpenStreetMap. But we have to see how this influences the FlexiGIS results, and this is the step that is currently going on. Furthermore, we were in the sprint one, we addressed challenge number 4, which is on we had this as an objective to improve the exploitation of the urban tab, for example, by the use of the world settlement footprint layers, and to investigate how we can implement a view or a scope on UTAP. I have to say the urban tab is developed within the department on land service dynamics, where we are also part of in DLR, and also the world settlement footprint layer is developed in our team. So it makes sense to have a close look to this. The objective of the UTAP is to bring together all kinds of users, data providers, service providers, end users, but it is not a data portal. So you cannot go there and just get your world settlement footprint layer from there. At the moment, it is really for expert users only, but there are quite some developments upcoming regarding the usability and also changes in the business model. And at the moment, our findings are so far that it's currently not suitable for implementing the pilot results. But there are a few interesting user stories for future implementations, where once it is clear which kind of EO data FlexiGIS will use for certain, and if the developments of the urban tab are closed as well. And then I think there is some promising user stories where maybe if it works out, there could be a service on urban tab, for example. Then we addressed challenge number 7, which is about the compliance with Inspire and other interoperability and geo data sharing principles. We were looking at the world settlement footprint, which, as I said, is also developed by colleagues in our team. And it is a freely available dataset. It can be viewed in UTAP, and it can be also reused within UTAP. And we are currently assessing the requirements that come from Inspire, and we'll give some recommendations how to reach compliance, because this is very useful for making this dataset available throughout different platforms. So some concluding remarks, what we learned or benefit from eShape so far as a result of the Sprint 1, very nice, was that we were able to establish a successful connection between the EO specialist and the energy modelers. And we were able to find some kind of common language and started our exchange. And I'm looking forward what will come out of that. That is really, I think, a good starting point. We gained a better understanding on how the UTAP can be made use of, and we gained better understanding of the Inspire requirements for our global data sets that we are producing in our team at DLR. And general benefits from eShape is that the knowledge collection, especially on the Confluence, is huge. We, for example, benefit largely also as a team or as a department from the summary of the diocese that was produced by Arminus. So I really must say this is a huge treasure of information. I hope that will be available for a long time. Okay, thank you very much for your attention.
Thank you very much, Wieke. If you have any question, we have time for a session of question and answer. So please go ahead. Okay. No questions, so we can move on. Thank you very much, Wieke, for your presentation. And now I leave the room to Ioanna from DTU for our presentation about the merging offshore wind projects.
So, hi everyone. My name is Ioanna, and I'm here to present the third pilot of our showcase on renewable energy. A little bit on myself. I'm a senior scientist at the Department of Wind Energy, and together with a team of colleagues, we are working on improving our services to the offshore wind energy industry. So I will now stop my video, and I hope you can see my screen. If not, please let me know.
It's okay. It's okay.
Perfect. So yeah, I just introduced the team. I will start by giving you a very brief overview of how we conceptualized the Pilot 3. And this is a borrowed slide from the kickoff meeting of eShape almost a year and a half ago. So our objective has been to provide Earth observation-based products to support the wind energy industry offshore, and specifically to make use of longer archives of winds observed from space from different sensors. And we have been doing this for a while now, providing wind resource assessment information for other European funded projects or Danish projects. And our target group has always been the offshore wind farm developers and operators, or consultants, or decision and policy makers. I will elaborate more on our users later on. So what eShape has allowed us to do is to refine both our, mostly our objectives actually. So the rationale behind the pilot is that winds observed from space can serve as a roadmap for a various big suite of points related to the offshore wind energy industry. And that includes climatological conditions of the wind environment offshore. They can help support the decision-making for installing more accurate in situ meteorological stations. They can also help the decision-making on how to plan and execute very high-resolution model experiments, and they can also support the validation of such models. So Pilot 3 aims at actually optimizing, improving, and advertising our existing satellite-based services. And the idea is to enhance the services we have already, and I will show them to you in a short time, but also to develop a new type of satellite-based wind product by tailoring or merging separate products right now. And of course, our key focus is to add value to the raw satellite observations and tailor them to the wind energy industry needs. And a big lesson for us is ongoing, is the co-design of these services with end users. So as a very brief introduction on what we are talking about. So we are talking about Earth observation data of winds over the ocean. They are based on microwave radar technology, and essentially what happens is that we have radar sensors flying around the globe, and they emit electromagnetic pulses, which then backscatter from the small scale waves on the ocean surface, and from that information, the wind at 10 meters above the ocean surface can be derived. So we are talking about two main suites of sensors. One is the synthetic aperture radar. So Sentinel-1 is the best known sensor for that. And you can see on the left side a very nice selfie picture of the first Sentinel-1A taken in 2014 when the platform opened up the solar panels. And then we also are talking about scatterometer winds. And the most famous sensor for that is ASCAT. Both are European sensors on European platforms, and they have different advantages and disadvantages, which I'm going to elaborate on very short now. So as I said, the basic principle is the backscatter of the radar signal from the surface of the ocean, and from that backscatter there is a relationship between the small scale ripples and the wind over the ocean, so we can infer the winds. Typical sensor advantages are complementary, as you may see from this slide. So synthetic aperture radar sensors have a very high spatial resolution, which we process to wind retrievals in the order of 500 meters. So very, very high resolution. We have a very consistent archive of Sentinel-1 data from 2014 to now, but we are also including in our processing chains Envisat SAR data from 2002 to 2012. So we are talking about a long archive. This type of data is extremely valuable for the coastal coverage and the very accurate spatial resolution. and we do need a prior knowledge of the wind direction to infer the wind speed. And this is something we do in-house at DTU Wind Energy. So we create our own wind retrievals. So now when we are talking about the other type of sensor, ASCAT, it's basically the same instrument, but because of some modifications in the operation and the operation, let's say, we can infer both the wind speed and the wind direction from the instrument. That's something we do not do. We directly use products readily available by EUMETSAT, so we get the wind product directly. So this product is relevant to lower spatial resolutions of in the order of 12 kilometers, but it has also a very long archive from 2007 up to now, and it's very consistent in terms of the global spatial coverage, but also the temporal coverage. So there's a lot of advantages and disadvantages, and the rationale of merging products from these two sensors is quite interesting for us. So what we do already, or what we have been doing already for a very long time now, is that, as I mentioned before, we obtain synthetic aperture radar information from ESA, and we in-house process them to retrieve the wind speeds, which are publicly available from this website here. We are having a consistent coverage of Europe, but we can also add new areas, or we are adding new areas of interest if relevant projects come up. So if someone follows this link, you can see an image similar to this. The user has the ability to select the area of interest, the temporal period of interest, and view SAR wind retrievals available. And also with by registering, there is a possibility to also download the individual files. So another of our existing services, and that's a demonstration service, is that we maintain a European offshore wind resource database, if you allow that title. And you can see here a screenshot from that website. This is ongoing now, maintenance and upgrades, but now you see how it looks up to now. So we are separating our wind resources into, let's say, SAR winds and ASCAT winds, and the user or the website visitor can click on the relevant heights and what the kind of sensor they want to view, and see a map of the wind resource, or the mean wind speed at least. There has been no direct access to downloading the files so far. That can be done by sending an email and we can provide the files to you, but we are looking on improving all these user functionalities. And as you can see here, there's different panels for the different options we show. So another option is another demo project, which is available on this same webpage. And that has been a test on deriving climatological significant wave heights as well, which could be relevant for the offshore wind industry. And that's something we would also like to explore. This is only for a test area of the North Sea, but it's a kind of service that we are willing to demonstrate to users and get feedback on that. So the developments we are planning for the for pilot 3, as I mentioned before, is to actually, beyond improving what we provide already, is to merge the different data sets from SAR and ASCAT into creating a unified offshore wind product in a way that we can improve potentially the temporal coverage, which is an advantage of ASCAT, with the high spatial resolution, which is the advantage of synthetic aperture radar technology. And here you can see just a conceptual derived mean wind speed map. And we are working on this as well. There's a lot of steps to be followed, but it's a concept we are willing to explore more. Just to demonstrate, for example, why we are so interested in looking at the offshore winds from Earth observation data as opposed to more traditional approaches, for example, from models. Here you can see for the west part of Crete, which is an island in the Aegean Sea, you can see a simulated 10-meter wind speed on the left panel, and you can see the satellite-derived wind speed on the right panel. The color axis indicates the wind speed, and they are scaled to be exactly the same. So what we see is that with, for example, this particular simulation, because of the topography not being as accurate or not being represented as accurate in the model, we have very coarse approximations or simulations of how the wind evolves, while with the satellite sensor with SAR, this is a Sentinel-1 image, we have very fine details of how wind changes because of the island's morphology. Another example is the wind resource map based on satellite winds from ASCAT on the left panel and for SAR on the right panel. And there's a mistake on the labels. They are both referred to 10 meters above the ocean surface, and that's something we have calculated for a European project called the New European Wind Atlas, where essentially what this kind of information shows you that, for example, we have very different ways of reproducing the wind variability depending on the spatial resolution of the sensor. So this is a key for us to kind of try to merge the two products. And another type of comparison we try to do within the same project, as I mentioned before, is how, for example, this Earth observation-based wind atlas is compared to simulated wind atlases. And here you can see the satellite-derived products on the left and middle panel, and they now refer to 100 meters wind speeds, which we calculate using a methodology to essentially lift the 10-meter winds to 100 meters, for example. And on the right panel, you see the simulated 100-meter mean wind speed as well. So what a visual comparison on that can show is that the satellite products offer much higher variability in how the wind changes, especially very close to land of complex coastal morphology. One very obvious part here, and I don't know if you can see my cursor, but we have a very consistent feature in the Gulf of Lions with the Mistral wind, which is very nicely represented in the satellite products, and it's a bit more blurred out on the right panel on the modeled winds. So, and then if we look at the very high resolution advantages of the SAR sensor in particular, you can see on the top left of this slide, the black and white panel represents the real radar backscatter that we, let's say, download from Sentinel-1. And then the right-hand side of the same panel shows the derived wind speed from this backscatter. The dots represent the actual wind turbines of a wind farm. And you can see that there is quite a fine accuracy and spatial detail, given that these are images taken from 600 kilometers above the surface of the ocean. And what we can see from these images is how the wind may change when it crosses a wind farm. And there's, just for a visual comparison, you can see the same timestamp retrieved from the same wind farm. On the bottom right panel, two figures from an actual ground-based radar, which was based on land and looking over the wind farm, over the sea. So we get information from the SAR sensor that could potentially be comparable with some assumptions to ground-based sensors. And that's very useful because it helps us validate and understand how good we are performing, and also how useful could the wins and supplementary could they be? So in terms of user involvement, we have had a prior experience of servicing the industry in in a very basic level, I would say. And we are currently having 4 users who have expressed their support, and 1 more may be onboarded soon. We have users who are quite active in monitoring such retrievals from Sentinel-1, for example, and they are happy to post them to their Twitter accounts. Here on the left, you see 1 example. Yet we have quite a bit to go until we reach the point of developing a consistent relationship with those users. And for that, the work package Do and Co-Design has been extremely useful because we have been having already a lot of support from them. That has allowed us to categorize our pilot in a type 2 pilot named as the technology push. So according to the co-design procedure, we are a pilot that looks for potential applications to the certain technology. We have an idea of what these applications may be, but as this slide can show, a major issue is that we have a presumed identity of how we can help the industry, but we need to somehow maximize the input from the industry to understand how we can better support them and make our products more interesting to them. So the status that we are on now is that we have been organizing this type 2 co-design. We have been presented with a set of methods, actually 3 methods of how to move onwards from where we are. We are in the process of analyzing our related stakeholders. So we have already planned user involvement workshops. We have already had an internal workshop with Work Package 2 partners, and now we are in the step of planning and materializing our stakeholder workshops. So our idea is that with their input, we will manage to understand better what is it that would make our pilot more interesting to them and work towards that direction. And for that, eShape has been very helpful because it has allowed us to tap into resources and ways of thinking that we have not had access to before. And with that, I would like to thank you very much for your attention, and I'm open to questions.
Thank you very much, Ioanna. So perfectly in time, thank you. Very interesting. So we have rooms for questions about the very presentation of Ioanna. And then we can start, if you want, an open discussion about the showcase renewable energy. So first, is there any question about the presentation made by Ioanna? Okay. Thank you very much. And now we can have a question about the world presentations and the showcase in general. So no one. I have Philippe, actually, yes, Etienne?
How do you want to,
just maybe you can introduce yourself because
yes, Etienne from Transvalor. I was just wondering if you don't get questions because we are now used to get a presentation at that General Assembly without too much possibility to interact with the microphone. So, okay, yeah. I was just thinking about that. Just for the sake of saying nice things, I am quite I think it's quite interesting that in the latest presentation there was an emphasis made on the communication with the users to actually develop the correct or the best product for their needs, which is a very good thing, I think, from a from my commercial point of view. Okay, that's I'm very satisfied to see that this is working. That the core design is working.
Yes,
But
indeed.
Yes, go ahead.
It's nice because it is one of the main aspect of eShape is about the co-design, and so we have a nice team with Pascal Lemasson, Benoît Veil, and Raphaël Barbier, who help the different pilots with respect this co-design with users, but also inside the teams for the development. So yes, indeed, for you, Torsten, it is important to understand that you have this at your disposal as a tool, very efficient tool, very interesting tools, following some methodology about co-design. But also you have some assistance in eShape about the user uptake, business model, and the aspect related to the DIaaS and the cloud processing platform. And actually, Torsten, maybe he's not, he has been disconnected because it was not clear for me if Torsten planned to, in his pilot, to use some DIaaS architecture, but he's not there to answer the question. Maybe Ioanna, you know.
I will know.
Yeah, Merete Badger from DTU. I'm involved in the new pilot with Torsten, and I can say we are going to look into the possibilities with the DIaaS. And one concern that we have always had is that we might get access during the project lifetime, but what happens afterwards? So we would like to fully understand that before we make a decision on it.
Yeah. This is the point, because it's new objects, the DIaaS. We understood by our research about this possibilities of having DIaaS that it's something on progress from the side of the DIaaS platforms. So it's not uniform at all. It's quite complex, and yes, so you can profit, as said by Wieke. We did a sort of review of these different DIaaS platforms, so you can look at this as a consortium member, and of course add some elements and some comments and feedbacks and updates following your proper experience on that.
That's nice. I'll look into that for sure.
It's very interesting, indeed. Okay, any other open question, comments?
I would maybe like to ask, I'm part of a pilot, pilot 3, but I would maybe like to learn from the other pilots how they have approached the users, and are there any good stories to share, successes or the opposite?
I would say, from what I have seen from the pilot we are involved in with Solar, it's inconclusive for the moment. I would say, in general, it might be usable. It seems to be rather expensive. It depends really what you store on the DIaaS, and for me, if you want to deliver something which is operating 24 hours a day, 7 days a week, etc., so basically having customers needing access to your pilot all the time, I found it in a first view quite expensive when compared to your own infrastructure. It seems to be much more expensive if you have to have the pilot open all the time. That's if you want to do some computations, okay, that's perhaps correct to use a DIaaS. But for continuous service, it might be a cost which has to be taken into account for a future commercial service.
Thank you, Etienne. But I think that the question was about the link between the developer teams and research and the users. We have we had some very interesting dialogue with the War Package 2 about the co-design. And of course, since we are doing some research, applied research, we are used to talk with users and end users. But here we have the opportunity to formalize our way of doing things and having a clear methodology, depending on the topology you saw during the presentations from Ioanna and from Stelios, that there are some different types of co-design. So there are sort of toponymy of co-design, and you can follow. And I think it's very useful to do things in a proper way. So yes.
So which type did you decide on for your pilot?
Yes, for the pilots, for the moment, we have first, it's a type 4 co-design. It's about the co-design with our team, because we have to discuss. In fact, the co-design is not only about the end users. It's also about the coordination between the different institutions and companies within the team. And so we had first a first co-design session that we have to follow with Transvalor to be sure that we are doing things in the proper way. And we plan to have the same co-design approach to merge in a way the two parts of the pilot 2. For the moment, it's separated. It's about, yes, in Oldenburg for the DLR part and Nantes for the Armin part. And we plan to have a co-design with DLR to better use the synergy. And for sure, there are some synergies. Yes.
Thanks.
Is there any other comments?
I would like to ask a question,
yeah.
Please. My name is Alalham. I'm working at the DLR in Oldenburg.
Yeah.
I have a question regarding pilot 2. When you assess the potential of BV at urban scale, do you consider that rather than the shadowing effects and parameters, do you take the facade, the building facade also into account, or just for the rooftop?
Okay, so this is a very good question, and for the moment we are looking only at the roof, but also we are of course able to, with the same exact methodology, not only focus on the roofs but everywhere as a surface. So we are interested in parking shades. We are interested in any other parts of the city, but considering considering the facade for the moment, the methodology is not exactly dedicated to the vertical facade. We have to cheat a little bit because it's a ortho digital surface model. And so it's a 2.5 dimensional information. It's a raster. So we have to imagine to have some additional elements to take into account the facade, but it's not foreseen within the E-shape activity.
I understand. Thanks. So I understood that it's doable, but do you plan to do it, or it will stay as an idea for further development?
Yes, for the moment it stays as an idea for further development. It has not been. You are the first one asking for that.
Okay.
We have
sorry.
some. No, it's very good. It's very good. Of course, we have thought about this, but we have some separate activities talking about buildings, and so for sure that we have this facade element into account. But for the solar cadastre, since it's a raster view, we do not have this in mind for the moment.
I see. Okay, thanks.
No, thank you. And for sure, the bifacial PV and things like that could be of interest for architectures and buildings. And so maybe we should consider this.
Ah, cool. Okay, thanks. Thank you very much.
Okay, if there is no other comments, I have took notes about the 3 elements, more or less 3 elements I want to report for the plenary session just after this breakout session. So I have if you agree, I have the idea to point the new pilots coming. So just a summary first, a summary of the pilots and the new coming in the showcase 3. And to stress the fact that he wants to have some feedbacks and user uptake activities as soon as possible. So this is the first point I want to stress, and maybe to for the next onboarding to stress that we need because we have already 2 solar pilots and 2 wind pilots having something about biomass or ocean mechanical energy, just to open to open the targets of the showcase about renewable energy. And a second point, I want to say that we have some already concrete element to be seen from the pilots. And Stelios and Ioanna, I saw that you have listed some web services and platforms. So if you agree, I can sit.
Yes, sir.
Ioanna, are you okay? Okay. So I have noted for you, Stelios, the solea.gr/solar-energy-management. And from you, Ioanna, I have noted science global winatlas.info, science.html, and sat winds, wind energy, DTU, DK, right?
Yep,
okay.
That's correct.
Oh, and the third point, it's an advertise, if you agree, about our Panagiotis and I. We will attend next week the Eurisi workshop about space for cities, and just an advertisement for this workshop, a virtual workshop for people to attend it. Do you have other points you want to stress for the plenary session?
Maybe for me, one point
could
be what it's already mentioned about the user uptake and the help of the horizontal structures of ESAPE in order to do what the proposal is saying, to actually help on involving new end users and because the number of pilots and the diversity of the science and service of each one of them and the subject, I think it's good to try to generalize it, but it needs I think individual attention. That's why this is a 4-year project, I guess.
Yeah, right. So the assistance we can get from eShape about user outtakes, co-design, JAS development, etc. Right?
Yes.
Okay.
Well, yeah. Yes.
Yeah. Go ahead. Okay. So any comments? Because it will start in 5 minutes, so I don't have many times left to prepare the slides. So if you are okay, I want to thank you everyone for this very interesting breakout session and discussion we had finally. And for people within the consortium, in 5 minutes, there will be the plenary session on which there will be some reports of all the showcases. Thank you very much, everyone. Thank you, Ari, for the assistance.
Thank you.
And we are looking forward continuing working with you on these pilots within this showcase. Thank you very much.
Thank you
very much.
Thanks,
Thank
Philippe.
you.
Bye-bye.
Thank you, Philippe.
Bye.